Now I hit from current slide. Okay. Can't think of any major announcements yet, but I'll just go over the ones I do. Math team still meets Fridays. Now, actually, what the math team's doing now on Fridays is going 11 till 1, and they're having it as a final review. For whatever class you're in, you can review your material for the final exam with the math team. And they're doing that Fridays 11 to 1.
What campus?
On the Birmingham West campus in C100. That's the science building that's in between the library and the B building. That little short hallway there, right near the library in C100. Mr. Rossi is the coach for that. And so they're doing that. Now, Monday afternoons at 3, they're still doing math team stuff, but the Fridays they're doing final reviews, which I think is really a good idea, nice thing to do. So you're welcome to go. Tutoring, not that I think you would need any, but you might be a great tutor, so you might want to consider checking.
I called up Gary's maybe a week ago, I think when first grade got out, and I asked her about becoming a tutor, and she was like, "They're good for this semester." So she said she told me to call her and talk to her fall to see if these classes.
Who is that, Dr. Davis? Okay, that was for the Space Center, right?
Just tutoring, period.
Well, you might try Student Support Services here. They do tutoring, but they're sort of separate from the Space Center. And Dr. Davis, I think, does mostly Space Center. Especially at the end of the term, there's always more demand for tutors than you have early in the term. So you might want to check with the folks. If no one's in 202 down the hall, go all the way down, take a left, and then on the right is 212, Miss Harris. And she may know if they need any extras. It used to be a Miss Hollins down in 202, but she moved on to another job somewhere. So no one's in there full time. There are sometimes people there. If you run into Miss Martin, Cicely Martin, she may have information on it too, but Miss Harris is the best one. And Miss Harris, the secretary, I don't remember her name right now, but she would also be good to talk with. Okay, and then the other two things. First, honors and awards is today, technically from 10 till sometime. 12-ish, okay. I hope it'll be done by 12. I need to be back here. Hopefully it'll be done before 12. And then but are you participating?
I work for the Space Center, so I have to.
Okay. Oh, so you work at the Space Center. So yeah, so that's probably the information you're getting on tutoring from that. Student Support Center also does now.
I actually go to investment.
What's that?
I actually go to investment and Birmingham.
Right, okay. Yeah, now Student Support Services on Birmingham is run a little bit differently, so I don't know. I don't know if they hire peer tutors. I know they have a full-time tutor, but I don't know. They may hire peer tutors too. I don't know. And another one might be, are you in the STEM program? You're not, okay, because they do tutoring also.
I don't know if Mr. Breeze is a terrible teacher.
What's that?
Mr. Breeze.
What about it?
He's a terrible teacher.
He's what?
A terrible teacher.
Yeah, I've heard that.
He really is. It's like he goes off subject.
Right.
He do a math problem and relate it to football, and he'd be on football the entire class.
Sorry. I can't really say much more about it. I hear what you're saying, and it's not the first time. I haven't heard that story before, but I've heard other things. And I see his student course evaluations every year. So, yeah, I know how they compare to others. And, okay. Sorry about that. Yeah. Okay. Oh, and the one other announcement is, normally, supposedly, I have office hours on the Birmingham campus on Friday, 7:45 to 11:45. As in most of this term, not this Friday, I've got an infusion tomorrow. So I'll be at the Kirkland Clinic if they need blood work by 6, if they don't need the blood work by 7, and then I'll be there most of the day. And shouldn't be driving very far after they finish. Very well. The only thing is it makes me so fatigued because in addition to just wiping out the white blood cell, dropping those counts like crazy, which is what it's supposed to be doing, it also has wiped out some of the red blood cells too. So I'm anemic and everything else, and I just get so tired so easily. But it's worth it for the white blood cells have not been this low in, well, I don't know if they've ever been this low yet. So.
In my biology, my anatomy 2 class, our slides had some leukemia.
Right.
And it was like this enormous increase of white blood cells.
Normal what?
Increase of
Yeah.
white blood
Yeah,
cells.
that one type of leukemia is that, right? And my way back, like 2008 or so, when my counts got, okay, no problem, okay. When my counts got up to 475,000, because they're supposed to be between 4,000 and 11,000, 475,000, they started the harsh chemo, which actually killed lots of things. Then my counts, white cell counts may have gotten real low then, but that was just, they bombed the system, and they didn't have these new drugs, these monoclonal antibodies. They had one, and my doctor chose not to give me that because he had had bad experiences with it. But then, that knocked it down for several years, and then when the old doctor retired, I got a new doctor, a younger guy. He loved the one the other one didn't like, so he put me on that, and that worked okay for a while, several years, and then he tried another one when it was losing effectiveness. It didn't do much better, and it was losing effectiveness. Finally, they got this new one, started in February. It's doing the job, and it's good.
Like this semester, you come to class maybe once or twice this semester.
What's that?
I say you come to class maybe once or twice this semester, and I said some must be literally wrong because you never cancel class.
Right.
And I was like, oh my God, I've been praying because I really love you as a teacher.
Well, thank you. I enjoy you as a student. You do a good job. All right, let's get going on math. Is there someone new coming in? No. Okay. All right. Let's even turn on the projector today. Why not? Okay. And we've been recording all that for 7 minutes. Okay, almost 8. Okay, what we're talking about is Chapter 2, polynomials and rational functions, and 2.4 is complex numbers, which is not in our, hey, here's Taylor. Okay. And I forgot to tell y'all on Tuesday that it's sort of a good news, bad news situation. The good news is today is Honors and Awards Day. Okay? That'll be over on the Birmingham campus, the Arthur Shores Fine Arts Building, which is the gymnasium. At 10 o'clock is when it officially starts, but people will have to be there, have to get there sooner. The bad news is, because of that, I'm required to be there, and I have to end class at 9. So we have a short, get over it. Okay. We have a shortened class today, so that's why I need to get moving on it. So what we're doing is complex numbers, and we talked about several of these things. And again, you're not responsible on the test for this, but you might run into it in the future. So let's continue with complex numbers, get as far as we can. If we can finish 2.4 today, it'll be good. If not that many people are here, you're not going to be tested on this, but you might need it in the future. Okay, any questions on anything we've done up till now? All right. The additive identity in the complex number system is 0, just like it is in the real number system. And if you wanted to write it as a complex number, that would be 0 plus 0i. Okay, that would be the additive identity. You add that to any other complex number, you get the same complex number. Furthermore, the additive inverse of the complex number, a plus bi, is exactly its opposite, minus, in front of parentheses a plus bi, which is minus a minus bi. Why is that true? Because if you add that to the original, you get a plus bi plus minus a plus minus bi. A minus a is 0, and bi minus bi is also 0i, and that's the additive identity. Just like, very similar to the real number system. Give me a number in the real number system. Any number.
8.
Second. 1. What's its additive inverse? -1. Exactly. Because you add 1 to -1, you get 0. Same thing here, except you do both the real part and the imaginary part. Okay? Here's example 1. We don't have to do this, but just to show you how easy it is, add the real parts, 4 plus 1, that's going to give you 5. Add the imaginary parts, 7i minus 6i is I. So it's, let's say, 5 plus I. Okay? And they go through all the steps here, and you get 5 plus I. It's really easy stuff. Okay? Again, 1 plus 2i plus 3 minus 2i. 1 plus 3 is 4. 2i minus 2i is 0. You get a real number, 4. So you can add two complex numbers together, you get a real number. Well, of course, real numbers are complex numbers with just no imaginary part. So that will be just simply, after they do all this, 4 plus 0i, which is just 4. Okay? You don't have to write a 0i. You don't have to write a 0 plus 7i. You just write 7i. Okay? And here's another one. Now, this is a subtraction problem. And here we have a pure imaginary number with no real part. And then you have subtracting from this two complex numbers. So let's see what we get.
Would that be 3? Would that be 6?
Say that one more time.
Would it be 9i? It would be 9i.
It's going to wind up being just negative 5i, if that's what you're saying. All right, we're getting here. Okay. Janisha's here. So the top part of the alphabet is doing quite nicely. The top 2 students are here. And the middle part's doing okay. 1 student's here. The bottom part is really hurting. Okay. So yeah, you're doing all this ahead of time. Let's see what you get. Here's how I think of it. This would be a plus 2, minus 2, 0. That's the only real part. So it's going to be 0. And then we have a plus 3i, a minus 3i. That adds to 0. And here you have just negative 5i. So that's your answer. Now, they do it, take it out, and by all means, if you ever have to do it, take as many steps as you need so you understand everything you're doing. But this will come out just being negative 5i. Just they do it all sorts of ways, but that's what you get. Okay? All right, Melva's here.
Nobody's here.
Wait. We are here. We are here. Okay. The important ones are here. Okay. Great. Whoops, wrong one. Okay. And again, you're not responsible for this. You won't be tested on this. But if you ever need it, this is how you do it. Here's one. Boy, this is a little bit more. We have an addition and a subtraction of 3 complex numbers. So again, I like to start with the real part. 3 plus 4.
Which is 7.
And this will be a minus 7, so the real part is going to be 0. In the imaginary part, 2i minus I would be what? I. And this would be a
2i.
negative I.
So it'd be 0.
0. Exactly.
So
All that added together winds up just being 0, which is legal in most states, okay? It's just 0, okay? So adding and subtracting complex numbers, just like binomials, okay? You just add the like terms, you might say. Many of the properties for real numbers are valid for complex numbers as well, including the associative properties of both addition and multiplication. They work fine. Even though we haven't talked about multiplying complex numbers yet, I don't guess we did. Cumulative properties of addition and multiplication, doesn't matter which order you do. Distributive property of multiplication over addition, All these things work just like they did in the real number system. Okay? Just think of them as a complex number as a binomial. Okay? Now, it doesn't have any variables in it, but, I mean, it could, but treat the real part as if it's, say, a constant, and the imaginary part as if it has this variable I. It's not really a variable, it's a constant, but just treat it like that, and it works. So here's how we multiply complex numbers. We didn't do this already, did we? I don't think so. Now, you can do it the way they do, which is perfectly fine, but shoot, we have the good old, how do we multiply binomials? Curses foiled again. The FOIL method, yeah. Look at this. A times C, AC. That's the first. The outer, A times DI would be ADI. There it is. The inner, BCI. There it is. Okay, or there. Okay, and then the last is BDI squared. Okay, and there you have that. Now the only difference here is, again, remember I is not really a variable, it's a number. It's a weird number, it's an imaginary number, not a real number, it's the square root of negative 1. So I squared is I times square root of negative 1 times square root of negative 1, which is negative 1. Okay? So that then makes a real part AC, and this becomes a real part because that becomes real when you square it, and that becomes minus BD. So there's your first term, and then you add these two together, AD plus BC, just like you add the innards and outers before, and AD plus BC times I. So that's how you do it. Don't memorize the formula, just follow it and do what it does, remembering always I squared is negative 1. That's what they say here. Rather than trying to memorize the result, don't do that. You should simply remember to use distributive property or foiling, because these are always binomials. You know, they're always just two. To multiply the two complex numbers, and remembering to do I squared is equal to negative 1 at the end. Okay? So this is pretty easy. Okay? Can't you just look at that and tell me what the answer is?
It'll be negative A.
That's the real part?
12I.
Plus 12I. You got it. It's just so simple. They distribute and do all that stuff, which is what you did. It's just you don't need to take that much time to do it. But if you need the time, do it. If it helps you see it better, take as many steps as you need. Okay? This one, we're just going to FOIL, all right?
6 times 4, which is 8.
8.
6 times 3I, which is 6I.
6I.
You're going to do negative I times 4, which is negative 4. You're going to do negative I times 3I.
Let's say that again. Okay, wait. This would be 6I minus 4I, just 2I, right? Okay. Yeah, and then you were going on to this one. Negative 3I squared. Well, I squared is?
1.
Negative 1. So negative 3 times negative 1 is plus 3. Here you had a 6, so that would be 9 plus 2 squared, I think it was. 2I. Write them down. I'm just trying to speed things along. But there we have it, just what you said. Oh, was that 11? Okay, I had forgotten what the first term was. 11. Yeah, 11 plus 3. 8 plus 3 is 11, right? Plus 2. Got it. Okay? So it's pretty easy to multiply. Foiling, no different from what you did with binomials. Except, remember the I squared is minus 1. Okay? So let's do this one.
It'll be 9 minus 6I, and then it'll be 6I minus 4I squared. Okay, work on that. Give me an answer while I'm marking Jayla here, right? Yes. All right. Okay. The first real part is 9, right?
Okay, 3 times 3 is 9. And then you have imaginary parts, the inners and the outers. And the outer is
9.
minus 6i, the inner is plus 6i. What does that add to? 0. Okay? And then the last is
4i squared.
positive 4i, okay, negative 4i squared, right?
13.
Okay? But then I squared is?
-1.
So that becomes
4.
plus 4. 9 plus 4 is 13. Whoa! You multiplied two complex numbers and got a real number.
13.
Huh?
13.
I can't hear.
13.
13, exactly. Okay, got it. Now, is there anything special about these two numbers that added two complex numbers that gave you a real number answer? Take a look at it. They're what? Okay, not quite inverse. Conjugates of each other. Remember back in multiplying binomials, if you did a plus b times a minus b, what did that turn out? A squared minus b squared, right? And then when you factored a difference of two perfect squares, a plus b times a minus b. Those are conjugates of each other, okay? When we did irrational numbers, okay, whenever you've done that in the past, if you had 3 plus the square root of 2, and say you were trying to divide that into something, oh, that's a miserable thing to try to divide. But if you multiplied that by 3 plus the square root of 2, the conjugate of it, then you got a real number. You got a rational number, okay? In fact, you got a whole number, okay? So same thing here. Anytime you multiply by the conjugate, this is called the complex conjugate, keep the first term the same but opposite the second term, okay? Then you'll get a real number, no longer a complex number. And let's see them do it. Just what you did, only it takes them longer. Yes, you got 13. And CJ is here. Okay? All right. All right, let's do D. What does it mean 3 plus 2i squared? 3 plus 2i, that's 3 plus 2i. Yeah, use the same thing, multiply it by itself. So let's see what we get here. 9, just like before.
6i.
6i.
Plus 6i.
So that's 12i.
12i.
Okay? And then finally, plus 4i squared. What's I squared?
5. 4.
Yes. Okay. The real part will be 5. 9 minus 4 is 5, but then you have plus 12i. Okay? So, you don't lose the imaginary part here, like you did with complex conjugates, but you still have an imaginary part. But it's just like squaring a binomial. You square the first, twice the product, and square the last. It's just when you square the last, it changes its sign. Okay? Just like y'all said. Takes them a while to get there, but there it is, 5 plus 12i. Okay? So, now they're going to talk about complex conjugates. Even though they showed one in an example, in fact, that's what they say. Notice in example 2c, the product of two complex numbers can be a real number. This occurs with pairs of complex numbers of the form a plus bi times a minus bi, called complex conjugates of each other. And conjugates are usually pretty nifty things to have anyway. If you ever go into trig, hopefully many of you will, you'll use conjugates there to simplify things. So you use conjugates in all sorts of areas. So let's do it in the generic sense where we don't put numbers in, but just put letters to represent any number. A plus bi times a minus bi, complex conjugates of each other. Multiply them. A times a is a squared minus abi plus abi, minus abi plus abi, and then minus b squared I squared. Okay? Well, this is just a squared. These two add to 0. every time. If they're complex conjugates, that the cross terms will always be 0, just like it was with a plus b times a minus b. The ab's disappear. And then you have a minus b squared times I squared. What is I squared? Negative 1. So minus b squared times negative 1 is plus b squared. Okay. Now, I've already said when you multiplied conjugates together, a plus b times a minus b, right? You got a squared minus b squared. So later, when you factored a squared minus b squared, the difference to perfect squared, you know that always factors a plus b times a minus b. Well, now if you look at this, remember we used to say the sum of two perfect squares can never be factored. Remember? It's in the real number system. But in the complex number system, this is a plus bi times a minus bi. So they can be factored, but not in the real number system. They're only in the complex number system. Okay. Now, why are we doing that at this point? This is how we divide complex numbers. Goodness gracious, can you imagine trying to divide by long division a number with i's in it? Oh, goodness, that would be miserable. In fact, maybe almost impossible. So how do we do it then? Well, we don't do it in long division form. If you're dividing a plus bi by c plus di, what you do, since you can't really divide by imaginary number, how do you do it? I don't even know how that's defined. Make this non-imaginary. Make it real. How do you make it real? By multiplying by its conjugate. But if you multiply the denominator by the conjugate, you must also multiply the numerator by the conjugate. Okay? Not its conjugate, but the conjugate of the denominator. So, your numerator becomes a times c, okay, plus bci minus dadi, that's the innards and the outers, and then a minus bdi squared, which is plus bd. That's the real part. There's the imaginary part. Just like multiplying any two complex numbers. But when you get to the denominator, c squared plus d squared. So if you fold that, the innards and outers add to 0, and then you get c squared minus d squared I squared, which is plus d squared. Now, that's a number. It's a real number. And you can divide this into that real number. You can divide that real number into that real number and keep the out. So you can divide complex numbers, but this is how you do it. Same thing with irrational numbers. You never try to divide by irrational numbers. That's really miserable. Multiply by the conjugate, and then you're dividing by a whole number. Okay? So here's an example of it. If you're trying to divide this by that, don't try to divide by imaginary. Multiply the denominator by its conjugate, but then you have to multiply the numerator by that same conjugate. Why? Because what's 4 plus 2i over 4 plus 2i? 1. And you can multiply 1 anytime you want to without changing the values. Okay? So up here you'll get 2 times 4, 8. 4i plus 12i would be 16i. Okay? And then you get?
Plus
negative 6. So 8 minus 6 is 2 plus 12i, wasn't it? Something like that. I don't remember. I'm not writing them down. But what do you get down here? This is easy.
8.
Say again?
No, you get 16.
16.
Yeah,
Again?
8.
Right. No, 16.
Oh, wait. Oh.
Plus 4. 16 plus 4. 20. There's your denominator. And then your numerator was whatever it was. Yeah, let's write them down. I'm not trying to take the time to do it. So it's 8 minus 6 is what we had in the numerator. So it's 2 plus 16i. That's what we had up there. The denominator just becomes the number 20. Now, the book is really picky about this. To me, that's a perfectly good answer. And I'm not going to be asking you for these. But the book always likes to write it in standard form. So that would be 2 over 20, which is 1 over 10 plus 16 over 20i, which would be 4/5 I. Yeah. So 1/10 plus 4/5 I. Actually, this isn't the best one because you can factor out a 2 for both of those. So if you had 1 plus 8i over 10, that would be okay with me, but then they always take it to the standard form. 1/10 plus 4/5 I. A plus B I.
So we could leave it as that 2 plus 16 I?
Well, number one, I'm not going to ask you to do this ever, but you would factor out the 2. Because this has a common factor of 2 and that has a factor of 2. All right, here's Chris. Okay? I know y'all are going to be so happy to hear my news later, but I'll wait till more people come in. Okay? Huh? Okay. Okay. Now we're talking about complex solutions of quadratic equations. This is why we're bringing this up now. Because if you think about this chapter has been dealing with polynomial and rational functions. So why did they introduce complex numbers in? Here's why. Because when you are solving quadratic equations, which remember, whatever you were doing before, synthetic division, whatever, you always get down to a quadratic and try to solve it. Okay? Sometimes that solution comes out being a complex number. Remember with the quadratic formula, you have minus b plus or minus the square root of, that square root is what's going to get you here, b squared minus 4ac, right? If that b squared minus 4ac turns out to be a negative number, you take the square root of a negative number, that's where you need your complex numbers. Now I'm going to try not to give you any like that because you technically aren't supposed to do it well. It's okay to do it, but there is a reason. Now they do something I don't like to do. I know they stick to their standard form, but frankly, when it's ambiguous, I say change the form. When you have a square root like this, square root of a negative 3, well, you can't do that in a real number system, right? Never take the square root of a negative number in the real number system. But in a complex number system, you can factor this to be 3 times the negative 1, right? And you can take the square root of 3 and the square root of negative 1. What's the square root of negative 1? Say again? I. Just I. Okay? So this will be root 3i. I don't like to write it in that form. Anyone have a guess of why I don't like to? Now, sure, with typesetting, you can tell that I is outside the radical. But when you're writing, sometimes that line gets a little too long, and you can't tell if the I is inside or out. So when I'm doing something like that, I always put the, let me get my pen activated. Say again? I put the I in front. I would write this as I root 3. That way it's not at all ambiguous that the I is not under the radical. It's not. It's outside the radical. So I like to do it that way. The book refuses to do it that way. It just does it like this. And they'll write it this way. And again, that to me is, I can tell looking carefully at that, but if I just glanced at it, or if when I was writing it, that line got a little too long, then you can't tell. Is the I under there or not under there? So I would always write this as I root A, and then it's very obvious. That's it. But the standard form is BI, not IB, Hey, you already told us it's commutative, so why not let it be commutative here if it removes ambiguity? But that's my little thing. Now, do you want to do a quadratic formula just for practice, or want to move on? Huh? No. I'm going to try not to give you. Now, if you're working homework exercises or working something on whatever you call it, WebAssign or something, they may have some problems like this. So, but, if you see one, just go on and skip it and go on to the next one. Do you want to do a quadratic formula or not?
Sure.
Okay. How do you do? Just to remind ourselves, how do you do first, can you factor that? I guess we ought to start there. Can you factor? No, I don't think so. That middle term is too small. I can't think of anything you can add factors of the others to do it. So we have to use quadratic formula. And how does that go? X is equal to, say again? Negative b plus or minus the square root of b squared minus 4ac. Is that what you said? Good, okay. Over 2a. Excellent. Okay, what is a, b, and c? A is 3, b is negative 2, and c is 5. Okay, let's see what our answer is then. There's the answer. Just fill it in, except you have to do a little math with it. What would negative b be? 2 plus or minus the square root of, what's negative 2 squared? 4 minus 4 times, what's a? 3. What's c? 5. I think you can probably already smell what's happening. Okay, over 6. Okay, 2 times 3 is 6. And this will be 2 plus or minus the square root of 4. Now, time out here. Here's what I do next. You know this 4, that's always a minus 4. And these two numbers always have some sign. First thing I do when I get that 4 written, the first thing written down, count the number of minus signs. If it comes out odd, like 1 or 3, you put a minus here. If it comes out even, one of them you know is always negative, then it comes out a plus. This is going to be negative. Negative what? 60. Okay? Over 6. Guess what, team? That's not going to be a real number. Okay? You cannot take the square root of a negative number in the real number system. But, and I'll go on and carry this one forward, though you'll have to. What is under the radical now? Negative 56. Okay? Over 6. Now, I'm just going to carry this out because to let you see it one time. We're not going to mess with this anymore. 2 plus or minus the square root of, I'm going to factor that 56. Okay? First thing I'm going to factor is the minus 1. Okay? Okay? Now, what I want to do next is find out if there are any perfect squares lurking around in there in 56. You know what your perfect squares are, right? What are they? 16 would be one, but 16 won't go into 56. Another one? A real easy one. So yeah, 2 times 2 is 4. Will 4 go into 56? No? Oh, it will? Okay. Okay, second? Yes, 14 times. 14 times 4 is 56, right? So we'll write that as 4 times 14, right? Okay, and that's all over 6. So this will be 2 plus or minus. Now, what's the square root of negative 1? Say again? I. Square root of 4 is 2, so I'm going to put the 2 in front of that. That's no ambiguity there. And then you have the square root of 14. Can't take any other perfect squares out of that, and then divide by 6. Well, now you notice both terms in the numerator have 2's in it. The denominator has a 2 in it, so you can divide out a 2 in both places and divide out a 2 here and be 3. And then the book likes to take that and call it 1/3 plus or minus, get out of there, and I write it this way, I root 14, if I could write, over 3. Okay? Now they'll put square root of 14i, which I find is hard to see. Okay. So there's my answer. Let's see what they got. Let me clear all my writing. Okay. Was that a good review of the quadratic formula? There they have it again, and again, and again. And look at that. I mean, it's just so irritating to me. They put the 2 out front, which makes sense. You could write the square root of 14 2i, but that would be really confusing. You wouldn't know if the 2 was part of the 14 or not. So they put the 2 out front. Well, why don't they put the I out front to make it clear too? But they then write it this way. Now, writing it this way, square root of 14 over 3, that's a little clearer with I down here that the I is outside that radical. So this one is okay that way. I still would like to write it I in front. If that was just 7I, no problem there. But all this other stuff, put the I in front of it, just to make it clear it's not part of the radical. Okay. But that's just my little pickiness. And that is the end of the slideshow. There are plenty more examples here, but we're not going to do them unless I don't even think it's worth doing the vocabulary. Do you think? Okay, there's no homework exercises in this section, so let's move on to 2.5. Okay?
So our test is going to be probably next Thursday.
What's that?
Our test will be next Thursday, probably.
Possibly. I don't know if we'll finish 2.5 and 6 by then. I doubt it, kind of, because we've got to do 2.5 and 2.6. And 2.5 is one of the biggest and maybe most important sections in this chapter. And 2.6 is a whole new subject, okay? So I kind of doubt it'll be Thursday. I think it'll be the following week. But let's see if we can get moving along. Okay, I'm going to give you all your quizzes back and all your tests back, and then those things at the end of the chapters, those summaries and things, that's a great guide. And then, why don't you make your own study guide, like a formula and equation sheet? That would be a good study guide. And the fact that you make it, that plants it in your head better than if I make it where you just are very passive about it. You're actively writing it down, and that puts it in your brain better than if I did it. Don't you think that's a good idea? Oh, I thought you would like it. Okay. Huh? Now, Polynomial Rational Functions, Chapter 2, Section 2.5, finding those zeros of the polynomial functions. We've been doing that. This section is going to be really dedicated to this. Here are our objectives. Use the fundamental theorem of algebra to determine the number of zeros of a polynomial function. We'll do that first. We'll find the rational zeros of polynomial functions. That is going to be a really handy tool. Something we haven't done yet, but it's really going to be handy. We'll find we're going to sort of skip over conjugate pairs of complex numbers. We already talked about it. We're going to count those as if we're not going to mess with them, okay? And we'll find the zeros of polynomials by factoring. And we'll use Descartes' rule of signs and the upper and lower bound rules to find zeros of polynomial. We're going to get all these tools in our belt. The whole purpose is finding zeros. And we'll find the zeros polynomials in some real-life applications. Okay, so let's start with the fundamental theorem of algebra. Okay, now what I was going to say, especially for you folks who came in a little late, I said it earlier, it's sort of a good news, bad news situation. For you, you might find the good news not as good a news as you thought. The good news is today is Honors and Awards Day at Lawson, which means there's a ceremony over on the Birmingham West Campus in the Arthur Shores Fine Arts Building, which is also the gymnasium, and they'll be honoring students, giving awards, that kind of stuff. Okay? The bad news is we have to end class early today because several people have to get over there by 9:30, so including me, so they canceled classes after 9 o'clock this morning. Classes will resume this afternoon. Okay. So, yeah. So the bad news is we'll have to leave 15 minutes early. So, glad you rushed to make it in. Okay. All right. I really am glad you're here. So let's talk about this. In the complex number system, every nth degree polynomial has precisely n zeros. Now remember what we said back in an earlier section. If you have an nth degree polynomial, the maximum number of zeros you can have is n. But you may not have n, okay? But in the complex number system, every one of those n zeros exists. Some of them may be complex. Before we were talking only about real zeros. This is important result is derived from the fundamental theorem of algebra, first proved by German mathematician Carl Friedrich Gauss. You talk about a prolific mathematician and physicist and scientist. He was. He really was. One of the most prolific of all time. I mean, sure, Newton and Leibniz came up with calculus. He added so much to calculus that he ranks right up there, close to Newton. Maybe not quite to Newton, but awfully close to it. And here is the fundamental theorem of algebra. It sounds pretty simple. If f of x is a polynomial of degree n, okay, n being greater than 0, it can't be a constant, okay, so if n greater than 0, then f has at least one 0 in the complex number system. Duh, well, of course you would think that would have to be true. What we're getting to, it actually has precisely n zeros, but this is where it comes from. He proved this in general and then added to it later. Okay, now, using the fundamental theorem of algebra and the equivalence of zeros and factors, you can obtain the linear factorization theorem. Okay, this is what follows that. So if f of x is a polynomial function of degree n, with n greater than 0, just like before, then n has precisely n linear factors, okay? And those linear factors would be, you could have a constant out front, a sub n, just some number, okay? But then you have x minus c1 minus x minus c2, times x minus c2, times x minus c3, times x minus c4, all the way up to x minus cn, with exactly n individual complex factors. Now, the reason they use c's here, these are complex numbers. But remember, all real numbers are complex numbers as well, right? So every one of these is a complex number. C1 through Cn are complex numbers. There are n of those that these factors would make up that polynomial function, with some constant multiplied by it possible. Okay? Now, if these are factors, then x equals c1 would be a solution, a root, x equals c2 would be, x equals c3, x equals c4, all the way up to x equals cn. So you do have that many solutions to it. Now, those are with complex numbers. Any of those complex numbers are real or fine. Here's the other thing. Some of these can be the same. They're not saying uniquely different. You could have 3 c's equal 2, or 17, or pi halves, or anything else, or even a complex number. Same one. So this includes multiplicity here. Okay? You have that many complex factors, which means you have that many complex roots. Now, it says, note that the fundamental theorem of algebra and the linear factorization theorem tell you only that the zeros of the polynomial exist. They don't tell you how to find them, okay? So those are called existence theorems, which are good for mathematicians, but for practitioners like us, they're not all that useful. You just know they're out there, you still have to find them. And that's what the rest of this section is going to be, finding those zeros, okay? So let's do example 1 here. The first degree polynomial function, f of x equal x minus 2, has exactly one 0. What is that 0? X equal 2, of course, okay? Set that equal to 0, solve that, add 2 to both sides, x equal 2. Pretty easy, right? Okay? But it fits the fundamental theorem of algebra and linear factorization theorem. Okay, counting multiplicity, the second degree polynomial function has how many zeros? How many? We know it has 2, but they could be complex. Okay, so let's see if we can find them. What would you do first? Say that again. Okay, absolutely. She went right to the core. X, I don't think that's quite right. That would produce no term in here. Be x minus 3 times x minus 3, right? Because that's a perfect square trinomial. The first term is a perfect square, the last term is a perfect square, the middle term is the product of their square roots, double the product of the square roots. Pull it and see. X times x is x squared, minus 3x is minus 6x, plus 9. Yeah. So that's you only have one real root, but it has a multiplicity of 2. It's x equal 3 and x equal 3. Okay. So counting multiplicity, it has exactly 2 real roots. Right? Now, whoa, let me erase my stuff so you can see what's happening. Okay? Now, that's called a repeated 0, because you say, well, wait a minute, x equals 3 and x equals 3. It's the same number, but that's okay. It's just a repeated 0, multiplicity of 2, you count it twice for the fundamental theorem of algebra, or linear factorization theorem. Okay? How about this one? What would be the first thing you would do? And what would you factor? X times x squared, say again? Plus 4. Okay? Now, if you're living in the real number system, that only has 2 factors. Okay? X and x squared plus 4. Because what we've always said, you can't factor the sum of 2 perfect squares. Not in the real number system. Now that we can include complex numbers, this could be x plus 4i, x plus 4, 2i times x minus 2i. So you have 2 more complex zeros. Okay? I'm not going to give you any, or I'm going to try to avoid those. But this does have 3 complex zeros. Only 1 real 0. The other 2 are complex. And, as they just pointed out, or they haven't pointed out yet, but they will, x equal plus 2i and x equal minus 2i, those are complex conjugates of each other. And when you have a polynomial function with real coefficients, any of your complex solutions are going to be complex conjugates of each other. We're going to run into that, but we're not going to deal with it. And I think we've just run out of time. So let's see. Let's just show this. They did the same thing we did. Then they factored it exact one more. It has 3 roots, but 2 of them are complex. So we'll start next time. That was example what? That was example 1. We'll start next time with the rational zeros test. Okay? Let me see if there are any exercises here that you can do. This is a long section. Try to do any of the odds 9 through 13. All 3 of those are at calcchat.com, 9's at calcview.
On what page?
That's on page 162. Okay, good deal. Sorry that we had to end class early today. Forgive me, please. Okay. Oh, you're so kind. So very kind.